All right, so the homework packet that you have has got, of course, the calendar on the front, and then the second page is some 3 songs that will have this unit. We'll do part of one today, and so we're going to go ahead and start with the notes. You have them as slides, okay? So I have them as this big slide here. You have them as little slides on your notes. So here we go. All right, so today we're going to be talking about the normal distribution. And the key to the normal distribution is that it comes into play when things are not distributed proportionately. For example, if I was to say, hey, somebody got a 61 in another class, but it was out of 70 points, okay? So 61 out of 70 points, how would that translate to this out of our grades out of 100 points? So you would then naturally do what? Your instinct is to do what? Good. 61 over 70 equals x over 100, okay? So that is your proportionate response. This occurs if every outcome is equally likely in terms of there are the same number of grades that go from 0 to 10 and the same number of grades that go to 10 to 20 and 20 to 30 and 30 to 40 and so on. And so if there were the same number of grades in each section, then you would have this uniform distribution that looks like this, okay? Do you think that grades, whenever students take grades, that they are distributed this way so that there's the same number of each grade, type of grade? No, probably not. How would those be distributed? More people are going to be having what kind, the what? The average. More people would have the average, okay? What happens as you get further out here to the high end? Good, you're going to have less and less, okay? And then what happens as you get way out here to the real low grades? Less and less. Okay, good. So we end up with a distribution that looks more like this. So this is truly the way that more real-life situations are distributed. That's why we want to focus on the probabilities related to the normal curve. We want to figure out the probabilities and the values with a normal curve instead of just doing things proportionately. Okay? All right, first, let's do a couple of things. Let's talk about them proportionately. So if you had a proportionate value, set of data, so suppose this is the grades being distributed proportionately. So that's from 0 to 10, 10 to 20, and then 20, and then 30 to 40, and so on. Went all the way to the 50s, okay? I've got 100 out here to the end. This is a height of 1 because what is the amount of data that falls in this box here? How much? Yes, you should have 100% of your data falling in this box. So if I was to ask you, what is the probability that you are one of the pieces of data that falls in this red section here, and that goes out to 0.4, so what would be that probability that you get in the red section? 40%, very good. And you naturally found that by finding that area, okay? And so you found that area because it's a rectangle, base times height. All right? So that's natural. You guys already know how to do that kind of thing. Do be aware that the heights of the pictures are not necessarily always 1. They could be, in this case, a half. But the fact that the height is 1/2, in order to still have 100%, notice what the base is. It's going up to 2, because a half times 2 is still your 100% of data. So my question is, what's the probability that you are, if I put all of this data in a bag, shake it up, what's the probability that I get something in the red section on this one? It'll be 70 because I am going from 0.6 out to 2, so that is a base width of 1.4, a height of 1/2, so 1.4 times a half makes me have 70% probability. Okay, so that is what we've got going on if those were proportionate, equally likely, but we know that we don't have that typically. And so we're going to have things that are more distributed, more real-world values will be distributed more like this normal curve. Okay? Now, the things that you will be asked are things such as, what is the percent of value between, or percent of data between this and that? What's the proportion of observations? How much proportion of observations is between this and that? Or maybe, what's the probability of finding this or something greater? These words are all pretty much mean the same thing. So I could interchange those when I'm asking a question. Find the percent, find the proportion of observations, find the probability of something. And so we want to talk about, how can you find the probability of something? Because look at the shape of this area here. If I have an area, in fact, let me show it to you on a picture of the normal curve. If I have, okay, so suppose I want to ask you, what's the probability of getting something greater than 2? Well, look at the shape of this area here. What can you say about the shape of this area compared to the areas we were looking at a few minutes ago? Yeah, is this a nice little rectangle like before? No. So that's a problem. We are not mathematically advanced enough to know how to find the area underneath a curve like this. Okay? In fact, this is the function, and that's kind of a weird looking function. It's a Gaussian, anyway, I kind of tried to look it up. Where does this come from? But this is a function that, if you graphed it, would be this blue line. You know how if you go into your y equals and you graph y equals 2x plus 7, what kind of picture would you get from that? A what? A line. Good. If I said, hey, go graph 2x squared plus 7, what would you get from that? Parabola, and so on. Well, this function here has this shape. In fact, I went in this morning and I put it into my calculator. I put it into the y equals on my calculator. I typed it in. There it is. And, of course, I adjusted my window so you could see it nice and pretty. And there it is. There is that normal curve. And what our calculator will do for us is our calculator will give us these shapes that are not square, that are not rectangular. You know, we might be wanting to know what this shape is here. Okay, well, this is a curve, and then we got all of this, you know. So that is actually comes from using calculus, by the way. You would integrate, and it would take the integral, so you would like integrate, and that's something you don't even need to know about. But on that resource packet that has all of these numbers were made using that calculus. When we punch things into our calculators, those come from using this function and integrating with calculus, okay? So that's why we use our calculator for a lot of these numbers or these tables, because finding this area is not something that we are mathematically advanced enough to do on a regular basis. Okay, moving on. So, let's kind of just talk about now some qualities of this curve. Where's the mean and the median? Right there at 0. What can you say about the value of the mean and the median? They are the same. Good. What do you think is going to happen to this curve if, say, that, see, this has standard deviation that is this wide. There's 1 standard deviation. Here's 2 standard deviations. Here's 3 standard deviations. That's how many there are in a normal curve going up. I mean, most of the data will be within 3 standard deviations up and 3 standard deviations down. But let's talk about what would happen if, say, I cut my standard deviations in half. So now, 1 standard deviation goes to here, 2 standard deviations to here, and 3 standard deviations to here. What's this going to do to this shape of this curve? How will it look different? Good. It's going to kind of, if you can visualize, like if you had a balloon, you know, and you squinch it in, it's going to pooch it up here and make it taller and skinnier because you need the same amount of data, but it has to go in this taller, skinnier, and narrower area. Okay? All right, so that is how this curve can squinch in and change if your standard deviations get smaller. All right. Okay, moving on. So, again, here are your basic the basic information about a normal curve. It's unimodal, symmetric. The mean is the median. And then I wanted to just give you some value, just give you some notation. Just remind you, we've seen these before, but I just wanted to stop for a moment. There are two ways that we will write our mean, either with a mu, which is a Greek letter, and that's if I'm talking about the mean of the population. X bar is also the mean of X, but that's if it was for a sample. Okay? For standard deviation, we've got this Greek letter sigma, the lowercase sigma, and that is for the population. And for a sample, it's just a regular letter S. Okay? See, we had Greek letters for those population, and they're called parameters, population parameters. If they're for the samples here, there are sample statistics. Okay. All right, just wanted to kind of give you a heads up on that. So let's now actually take a look at what calculus has calculated for us. Taking that function, finding what is, now look at what here on the bottom it says, mu minus sigma up to mu plus sigma. What does that mean? Okay, 1 standard deviation down to 1 standard deviation up. How much percentage of data is in there? Yeah, 68%. So in this white section out here, and here is the rest of the 100%. Okay, so 68% is within 1 standard deviation. Next, 95% falls within 2 standard deviations. And again, this comes from that function that the calculus calculated for us. And 99.7% of observations fall within 3 standard deviations. Okay, so that is actually known as the 68, 95, 99.7 rule. Imagine that. That's so creative. I would imagine that they keep it that just so that it reinforces those numbers, so you keep remembering what they are. 68, 95, 99.7. Now, it also, in some textbooks and some professors and such, and I know that my dad, whenever he talks about this, he refers to it as the empirical rule. So that's a nice shorter way to say it. So the empirical rule is that 1 standard deviation is 68, 95, and then 99.7 for 3. Okay, now I want us to take this picture and not only know what's in that 1, 2, and 3, I want to section off each individual section and look at what's percentage of data is in each section. And now that we know what the calculus has given us with the 68, 95, and 99.7, you should be able to figure out the rest using your adding and subtracting of areas. So let's start with this middle section. If I know that from here, -1 standard deviations to +1 standard deviations is 68%, then how much is in this section right here on the left side of it? Good. So this has 34% in it. And so then what's here? All right. Now, you are going to figure out the rest. You're going to figure out how much is in each one of these other sections by using your knowledge of how to get, all the way across is 95%. So if this has got 95% across it, but I've got 68% already accounted for, then I can figure out what's left in the sections. I'm going to take just a moment and let you see if you can't compute all of the rest of those sections. Okay. Let's see what falls in those areas. Okay, so from 1 to 2, how much data is that? Good. -1, -2 to -3. 2.35, and there is still a little bitty bit out here below 3 standard deviations. 0.15 of a percent. So not even 1/5 of a percent. Okay, good. And then, of course, these are symmetrical, so these sections up here have the same amount. Okay? So, if you are in the top 5% of your class, if you're in this top 5% of your class, then you are how many standard deviations above your classmates? This section here is 5% altogether. So you are 2 standard deviations and up above your peers. Okay? If you're in the bottom 5%, you know, then you're in this section here. Okay. All right. Now, with those knowing those percentages, now we're going to kind of put some real world data to it after we talk about percentiles. A percentile is just another way of saying the area that is below that, you know, that data. So if you go to the doctor and they say you are in the 16th percentile, then if they say your height is in the 16th percentile, then you are 1 standard deviation below the mean, because this is 16% of data down there below that. Okay, if you are in the 84th percentile, then that means you have 84% of people shorter than you of your age category. Okay, and so that would mean you are 1 standard deviation above the mean if you're in the 84th percentile. If you're in the top 10%, then you're somewhere over here. We haven't actually labeled where that is. I think it's 1.645 standard deviations above the mean. Okay, but that's something later we'll get to. Okay. If you're in the top 10%, that means up here is 10% with how much below you? Okay, so 90th percentile. All right, now we're going to do some real world stuff. So let's put this context to these problems. Assume that the heights of college women are normally distributed and they have a mean of 65 inches and then standard deviation of 2.5 inches. Do you think that it makes sense that the farther away you get from the mean, there's less and less people in those sections? Yeah, I think so. Okay, so I want you to put the context on here. For example, label right here at the mean would be what? Our 65 inches. And so 1 standard deviation above would be how much? 67.5 inches, because I added up a standard deviation. Okay, so label all of those values there. Okay, so I labeled what is in this picture. So I put that we've got, it's the height in inches of college women. Okay. All right. Okay, moving on. Now we're going to ask questions about that. So what percent of women are taller than 65 inches? And these are quick answers, so I'm not even going to write them down. What percent of women are taller than 65 inches? Good, 50. Next question. What percentage of women are shorter than 65 inches? Good. Next, what percentage of women are between 62.5 and 67.5? 68. How do we know that? Yeah, the empirical rule, or that 68, 95, 99.7 rule. Okay, good. Because that's 1 standard deviation out. Nice. Next, what percent of women is between 60 and 70? 95, because that is 2 standard deviations out. All right, now look here at this one. Here we have between 60 and 67.5. So here you're going to have to think a little bit differently. It's not just a straight up regular number. So I want you, there's a couple different ways you could come up with this. So think about that one for a second and see what you come up with. How much? Nope, not 40. Well, I know, yeah. Yeah, see, I know this section in here is 68. Okay, so I know all of that's 68 plus, right, so this is 68, and then I've got this other section here, which is, how much is that one? Okay, good. So we know that that one's 13.5, so that puts us at a total of 81.5, okay? All right, good, moving on. How about this one? What percentage or what proportion of women, what's the probability of finding a woman that is shorter than 70 inches, a college woman shorter than 70? 97.5. How'd you get all of that so fast? Did you add up all of those ones that we know? Okay. You could. You could add up all of those ones. I mean, I know this takes me to 50 plus 34 plus another 13.5 or whatever. Okay, so I could do that. Or what's another way? Yeah, how much is this section that it is not? So it is not the upper 2.5%. So if it's not that highest 2.5%, then it is the bottom 97.5%. Okay? So you've done these kind of area adding and subtracting and all those kinds of things, probably since 7th grade or maybe even before. Okay, so hopefully that's something that you can catch on to and find. All right. Now, all of these ones that we have done so far have fallen on a solid 1, 2, or 3 standard deviations above the mean. Do you think that all women are exactly 1, 2, or 3 standard deviations above or below? No, you have all these ones that are different standard deviations away from the mean. So let's address that because that's a big deal. So here we go. Here's an example. We want to find out what happens if the value is not an exact whole number of standard deviations away. So here's the example we'll play with on this. So after 5 weeks of class, Ileana must transfer from a stats class at Lanier to this class. Well, last week was the Chapter 1 test in both classes. Ileana scored a 61 out of 70 on that test at her school. But let's say our test was out of 100 points, not 70. So what score should we give her? Okay? And as we talked about at the beginning of class, it is tempting to do what? Your proportions. And why is this not a good idea for grades? Are grades distributed proportionately where every grade gets the same amount of students? No. So that is why this is not an ideal representation of how to get her comparable grade at another school. Now, do I think I'm going to do that on a test? No. If I was doing a whole GPA or that kind of thing, this could be something I would want to consider. All right, so since the grades are most likely normally distributed, we need to address that. Now you have, as the last slide on your notes there, a blank, one of these normal models, okay? So I'm going to give you some facts. It's actually at the top of your next page, but so that you don't have to turn, we'll all show you the facts. So we know lots of information about Lanier, and we know information about here, the Alito test. So here we go. The average score for Lanier's test was 50.5. Okay, so here's Lanier's average. And the standard deviation for Lanier's was 8.8. So the standard deviation for Lanier's was 8.8. So I want us to put on the normal model the data for Lanier. So let's come down here where you have your little normal model. And I want you to put the data for Lanier High with the mean and that standard deviation. Okay, so there are the scores with a mean of 50.5, standard deviation of 8.8 for Lanier. Okay, now I'm going to do the same thing for the Alito distribution. I'm going to put it right here underneath it. So let me go to the facts. So you have the facts. The facts are that our test score was out of 100 points, and it had a mean of 77.2, and our standard deviation was more varied, was 9.7. Okay, so let's go around here, and let's start with 77.2 and go with the standard deviation of 9.7 to find out the rest of those data values. Okay, so there's the grade distribution for our comparable test here. What was Ileana's grade again? Do you recall? Okay, at her school, her grade was a 61. So there's Ileana's grade right there. Okay, so she was a 61. So see, it's somewhere not on a solid standard deviation. So I want to give her her grade relative to how her peers did. How do you think I can do that? Ideas. How can I give her a proper grade based on that information? Okay, I could use the percentages. Then I'd have to like figure out what percentile she's in. Okay, I don't have the tools to do that right now. Other ideas? Okay, you're on the right track. Gracie said figure out how far she is from the highest grade and then do that to the other one. So we don't want to just straight, like say she's 20 underneath the highest grade, take away, or 9 under the highest grade, take away 9 and give her a 91. That's not appropriate. But we can compare her. Go ahead, Cameron. Oh. See, and I still don't think that that's going to work. I still think that... Okay. No, that would still be given a proportional relationship, given that. It would still that if you're setting up a proportion. Go ahead. Let's try one more. You were close when you were talking about how far she is from the highest. Let's compare her to the average. Let's see how far away she is away from the average score at her school, and then put her at that same distance away from the average score at our school. So that means I would do something like this. I would say, oh, she is 1 standard deviation up and a little more. So she's a little more than 1 standard deviation up at her school. Well, I'm going to put her a little more than 1 standard deviation up, that same amount, up at our school to find out her grade here. That number of standard deviations that you are above the mean is called your z-score. You can see on one of your slides it has the z-score definition is that number of standard deviations that value is away from the mean. I skipped a few slides to get to it. But by definition, the number of standard deviations that value is away from the mean. And so basically we are figuring out how you relate to the average. So look here. Here's her relative position. She takes her score, compares it to the mean, the class average, and then divides by the standard deviation to see how many standard deviations there are. So x minus the mean over the standard deviation, x minus the mean over the standard deviation. So that is how we can find Ileana's relative position for her school and then put her in that same spot here. That is called that z-score. So let's do that. Back here, let's find Ileana's z-score. So at Lanier High School, she scored a 61. That's the x minus the mean at Lanier is 50.5 divided by the standard deviation at Lanier is 8.8, and that is a value of 1.2. It's actually like 1.1 or 1.196, something like that, or 1.195. So she is 1.2 standard deviations above the average. 1.2 standard deviations above the average. So if we look down here at the bottom, she is located 1.2 standard deviations above the average. So now how can I give her a grade here? Good. Take our score, our average. I want her to be 1.2 standard deviations above our average. But which standard deviations? Their standard deviations or our standard deviations? Ours. So here is our average. I want to add up 1.2 of our standard deviations, which were 9.7. So I'm putting her 1.2 standard deviations above the mean here. She was 1.2 standard deviations above at Lanier, and she will be 1.2 standard deviations above here. That puts her a grade of 89. So gives her a comparable grade relative to her peers, relative to how the rest of the group performed. Okay, and then I kept that relationship the same so that it's the same location. All right, very good. So now let's finish out one other problem here, this one, and then we'll go on to the assignment. So here we go. Suppose that a student has taken 2 quizzes in a statistics course. On the first quiz, and I like to kind of put these facts down as I read. On the first quiz, the average was 32. The standard deviation was 8, and the student received, that's the X value, a 44. Okay, so that's what was received on the first quiz. On the second quiz, the student got a 28. What letter is that? What is a 28? That's your X. Good. And for which the mean was 23 and the standard deviation was 3. Okay, so how can I tell which quiz the student performed better on relative to the rest of the class? Find the z-score for both quizzes and see which one was better. So do that. Find the z-score for each quiz. Okay, the first quiz is a z-score of 1.5. Second quiz is a z-score of 1.7. Which one did the student do better on? The second one. Why? More standard deviations above the mean. That is why. Student did better on this one because there are more standard deviations above the mean. Okay, very good. So now that's the end. There is another example about salaries, but it's comparable to what we just did, so I'm not going to go over that one. I'm going to have you start this so that I can walk around and help you and guide you through that. So